Alright, welcome everybody. So I told you that today we would talk about solution stoichiometry and also that I wanted to go through, the types of reactions. So let's first talk about the 5 types of chemical reactions. The first kind being a combustion reaction, which we'll cover again when we do organic chemistry. And we did this when we did combustion analysis. So you'll have your compound that's going to combust, like a hydrocarbon, for example, something like methane, CH4. And it will react with oxygen. That's a key, ingredient in the reaction, reactant in the reaction, and then we'll produce carbon dioxide and we'll produce water. And this is considered complete combustion. If it was incomplete combustion, you would also form other products, like you could form, for example, carbon monoxide and water, which is why some of the home heating systems and using certain stoves, leaving them on can produce carbon monoxide. That's why you have those carbon monoxide detectors. And then you could also even produce carbon and water as well, and this is when you would produce like a black sooty substance. That's your pure carbon being formed. So the other 4 types, we have a composition reaction. That's where you take 2 elements like sodium and chlorine, and you combine them together and you form sodium chloride. So elements forming a compound. A decomposition would be the opposite of that. You could take, like your water, for example, and you could break it down into hydrogen and oxygen. Now, importantly, the AP exam expects you to know some specific decompositions. So what are some specific decompositions that you should really be aware of? Well, the first one is with chlorates. So if I have a chlorate, when that breaks down, it doesn't completely decompose. It's a partial decomposition. You'll form chloride and oxygen. Another partial decomposition that's important is one that we talked about in class, where you have a metal carbonate. And that does not completely decompose. That breaks down into the metal oxide and carbon dioxide. And finally, another one that comes up quite a bit is with hydrogen peroxide. This one does not completely decompose. It breaks down instead into water and oxygen. Hydrogen peroxide is kind of a cool one because we can catalyze that with some potassium iodide. Catalyzing it gets it to happen much, much quicker. You generate a lot of oxygen. If you saw the pumpkin vomit last year from me, you have experienced the catalytic decomposition of hydrogen peroxide. Hopefully one of you will bring in a pumpkin this year, and I can also demonstrate how that works. We'll give you details in class about what kind of pumpkin to bring in. So a single replacement. With a single replacement, you have an element such as, for example, could do aluminum, and we have a compound such as copper chloride. This is aqueous, and that's important. This is solid. It's also important because when we want to see this reaction occurring, what will happen is as we put the solid into the aqueous solution, we'll produce a new solid and a new aqueous solution. I haven't balanced any of these equations. You can go through and balance them yourself, practice that. But what happens in this particular experiment is the copper chloride is a blue color to it. And when we add the aluminum to it, you'll form like this solid copper looking substance because it is copper. And you'll have the solution turn from this blue color to a colorless solution. And then finally, there's double replacements, which we're going to spend a lot of time on in this chapter coming up for chapter 4, and that's where you have 2 compounds that are both aqueous. So you'd have something like sodium sulfate, that's aqueous. And then you'd have something like a barium chloride solution that's also aqueous. And when we react them together, we'll form the barium sulfate compound. That'll be a solid called a precipitate. And the sodium chloride will come out also aqueous in this case. So we form a solid from 2 soluble compounds. So it looks kind of magical when you do this because you are pouring together 2 colorless, usually colorless, and transparent solutions. And then all of a sudden, out of nowhere, very, very quickly, which is why they call it a precipitation, you form this solid. And that solid comes out of nowhere. And over time, if you leave the beaker sit on the table, it'll settle to the bottom and you can see the solid that has formed. Alright, so let's get to chapter 4 here. So these are the goals for chapter 4. If you want, you can pause the video or you can take your time to read through the notes and through the list and see what I expect you to be able to do for chapter 4. This is all required by the AP. Some of it's required by the IB, but this is definitely IB overkill here. So let's get straight into some definitions about what it means to be a solution. The reason why I'm going through this is because I really want you to understand that these reactions are occurring in water. And so we have to sort of know the terms that go along with the water solutions and be aware of them and be aware of how substances behave when they're dissolved in water. And so if I have an aqueous solution, I have water as the solvent. So water as the dissolving medium, which we call the solvent. So water is the solvent. It will dissolve the solute, and the solute, that is the substance dissolved, it can either be soluble or insoluble. And so if we're soluble, that means that the substance will dissolve. So this could include all types of substances. We could have salts like NaCl. We could have something like sugar, C6H12O6, although that's really temperature dependent. And then we could have substances that are insoluble, which means that the substance will not dissolve. Or at least it won't dissolve appreciably. And so some examples that you might have learned if you memorized Table F and took the SAT subject test last year, things like AgCl, BaSO4. So these are salts that I would dissolve in water, and honestly, when you dissolve them, it looks like nothing happens. It looks like they just fall to the bottom. When we do solution equilibrium, you'll see that some does dissolve, but it's very, very small molar amounts, pretty much invisible to, just looking at it. So two terms that are really important are electrolytes and what their properties are. And so an electrolyte, if I were to define this is a substance that is either an acid, a base, or a salt. And so these substances, they could either be ionic or they could be molecular. Hold on 1 second. Okay. So a substance can either be an acid, base, or a salt, so that means that they could either be molecular or they could be ionic. And we'll talk about that more on the next page. But, if you are an electrolyte, it's important to note that this substance will dissolve in water. It'll form ions. And once it forms ions, these ions are free to move. And once I have ions that are free to move, the key property of them is that they conduct electricity. So that's what I'm looking for in an electrolyte. And so we'll talk on the next page the difference between, what it means to be ionic versus molecular. How do you know when you are, an electrolyte versus not an electrolyte? So let's do that right now. Ionic versus molecular compounds. And so if I have an ionic compound, The first thing is that I would take an ionic compound like NaCl, for example, and when I put it into water, it'll form ions, it'll break up. Now these ions, they can move around, they're free. They're going to interact with the water, and we're going to show this on the previous page. And when they do this, these free ions, they're going to act as electrolytes. So you really need an ionic compound in order to do this. If you don't have an ionic compound, then you're not guaranteed that you're going to be an electrolyte. And the other type of compound that will dissolve in water would be a molecular compound, and let's see what I mean by like not guaranteed to be an electrolyte. So, the first thing is that you could have two types. You have the ones that are electrolytes versus the ones that are non-electrolytes. So the ones that are electrolytes are acids and some bases. Acids, for example, if I were to put them into water, like HCl, it would break up into ions. And those ions would default to behaving ionically. They would act as electrolytes. I could do the same thing with bases like NH3. When that interacts with the water, it again forms ions. And again, those would act like electrolytes. But most molecular substances are not electrolytes. They're things like, organic compounds that are somewhat polar. They'll dissolve in the water, things like sugars or alcohols. Let's do an alcohol, C2H5OH. So I put this alcohol into the water, and when it dissolves, it stays together. So it forms C2H5OH. It doesn't actually break up. Now, one last thing that's important is that some bases are actually ionic. These are those metal hydroxides. And so since these are ionic, these will act as electrolytes. We'll parse more about what a strong electrolyte is versus a weak electrolyte in a little bit. But let's go back to that previous slide here and look at, what happens when, an ionic and a covalent compound when they dissolve in water. So, it's important to note that if you have an ionic compound, it's bonded together with itself. And then, the first thing that would have to happen, step one, is for this to break apart into ions. You also have water. And water, as a liquid, it has hydrogen bonds. So step two would be for the water to break its hydrogen bonds. So you'd have water with some broken hydrogen bonds. Now step three is where they form their solution. With step three, the sodium and the chloride would come together with the water. And we'll do more of this in bonding, but just to give you an idea, if you have your water, the sodium is positive and it'll interact with the oxygen, and the chloride is negative and it will interact with the water's hydrogens. Now, if I compare this to something that would be like a molecular substance, something like methanol, which is very soluble in water. So I still have to go through the same steps, except here, one, I would still have my CH3, no ions, but I would have broken some hydrogen bonds. And for my water, I would still have the same thing above, where I would still have my water, but again, I'll have some broken hydrogen bonds. And then I have my third step, which is where I form my solution. So in step three, now I'm going to have a new mixture formed where there's new hydrogen bonds formed. Maybe what you could do now is pause this video and you can take a second to actually go through and say, what would those new hydrogen bonds look like? See if you can do it. The same way I drew the sodium and the chloride up here with the water, maybe see if you can do that down below with a methanol and a water molecule. How would those interact? Okay, so The next slide that I want to show you is strong versus weak electrolytes. Must have inserted a slide here. Strong versus weak electrolytes. And so I describe the term electrolyte. If you go back and look what it says that it's a substance, it dissolves in water, it forms ions, and then it conducts electricity. Well, what would be a strong versus a weak electrolyte? Well, there are certain substances that are strong electrolytes, and these strong electrolytes are ones that fully ionize. These are characterized by either soluble salts, soluble ionic compounds, strong acids, or strong bases. These are the substances that will act as strong electrolytes. Soluble salts will go through the chart. That chart is missing. Okay, we'll go through the chart. I'll do that in class with you. But the soluble salts, these are ones that are needed to be memorized by you. We'll talk about them tomorrow. Some of them include, for example, nitrates like NaNO3, certain chlorides like NaCl. Strong acids, there's a list of them. There's 7 of them. HCl, HBr, HI, HNO3, H2SO4, HClO3, HClO4. All of these strong acids, they will ionize 100%. The strong bases, these also ionize 100%. They ionize completely. They include the group 1 hydroxides and the group 2 hydroxides from calcium and below. So, for example, calcium hydroxide would be considered a strong base. The weak electrolytes, these are slightly soluble salts. These are weak acids and weak bases. So see if you could list, maybe 2 each of the acids and 2 each of the bases. See if you can figure out 2 weak acids and 2 weak bases that would fall under this category. The thing with the weak electrolytes is that, yes, they dissolve to some degree. The acids and bases, they will completely dissolve. They just don't ionize. So these are soluble, but not ionized completely. So that's the big difference between the slightly soluble salts. These don't dissolve well. Any of the salt that does dissolve will ionize. Any of the salt that does not dissolve will not ionize. Weak acids and weak bases, those dissolve, and yet when they dissolve, they don't actually ionize. So there's a difference there between them. So when we get to class, we'll talk about this table, this solubility chart, that is supposed to be here, but somehow or other it's not. And so I'll distribute a hard copy to you tomorrow. You can sit down and memorize it because you're going to need to know the solubility chart. So, a big part of this chapter is how do you know when something actually precipitates? Well, if you had the solubility chart up here, you could look and you could see if it's soluble or not. Hopefully you've seen a solubility chart or you remember what it looks like. But, let's look at this, for example, like PbI2. How do I know, that it would form in a reaction? Well, let's say that I had a salt, sodium iodide, and I react that with another salt like lead nitrate. Both of these are aqueous. They're soluble. They dissolve completely. They're strong electrolytes. I dissolve them and there's a double replacement. Go ahead, take a minute, write down what the products are. Hopefully, when you restarted the video, you got this PbI2 and then NaNO3. If I balance it, I would put a 2 here and a 2 here, and I'd have a balanced reaction. So here's my balanced reaction. When I look at this, I would need to use the table up above that I memorized. The table, what it should say is that most halides are soluble. Except certain ones where there's an ion, a metal ion, combined with it. Those include lead. Those include silver. Those include mercury. Mercury 1. In this case, lead is combined with iodine, a halide. That makes this a solid. It will not dissolve in water. It's actually this really bright yellow precipitate that forms. This is aqueous. Now there's a lot going on in this equation, and what would be really nice is what if we could actually, distill this down to, to what we actually would see in the reaction. And that's what we're going to do, tomorrow in class. Tomorrow in class we're going to sit down Wednesday and Thursday this week, and we are going to look at how to write this in a more effective way. In the meantime, I'm going to try and import another version of this that has the diagrams in it so that as I'm going through, it'll make more sense. All right, see you tomorrow. Thanks.